All right, welcome back. So this is our second on projectile motion. I've got 4 new things that I want to do today, and then I'm going to go back over all the stuff we did before the break. So we're supposed to find the slope of an arc, find the velocity vector, create an equation for the trajectory. So that's sort of y in terms of x instead of y in terms of time. And then figure out the angle at which we should fire something in order to get to the right height at the right time. Okay, so before we do all that, I'm going to go back and review everything we've already done. So starting with our scalar versus vector. So a scalar quantity is when you only have magnitude, you don't have direction. So if I just tell you 4, that's a scalar. If I told you 4 units to the right, then that's a vector because we also have direction.
Oh.
Um, our equations for the equations that I gave you are distance equations. If we wanted to make those vectors, then they would become displacement. Our sample units would be meters there if we're going to use metric. If you were in English units, this could be feet or miles or something like that. If we derive a distance equation, you'll get a speed equation. If you derive a displacement equation, you'll get a velocity equation. Hey, sir. So our units for the derivatives would be meters per second. If you derive a velocity equation, you get
What?
acceleration. So that would be meters per second squared. We started with a velocity vector. So if we have a velocity vector, we can break those down into components using sine and cosine. And then we can use those components to create our horizontal distance and vertical distance equations. Because there is no gravity acting left or right, our horizontal distance equation is the same as long as there's no wind or anything else that's causing us to accelerate left or right. Our vertical distance equation, however, does depend on gravity. So we've got this extra term here of 1/2 at squared. That a is your acceleration due to gravity. As long as you're on Earth near the surface, that acceleration due to gravity will be negative 9.8. If you're not on Earth and you aren't in one of your homework problems this time, then I will tell you what the acceleration due to gravity is on wherever you are. So for your homework, I believe you're on the moon.
Okay.
Any questions on any of this stuff from last time?
Mr. Brandon.
Yes.
So, like, will this video upload it again on like YouTube or?
Yes. So
Okay.
this will be uploaded both to YouTube and to my personal Chinese file sharing service. So the file sharing
Okay.
service will stay open for, I believe, 72 hours. But the YouTube will be up
Okay.
forever. Okay. So the key point here again is we can just derive these equations in order to work our way down this chart. So these are distance equations. If you derive them, we'll get speed. Derive them again, you'll get acceleration. Okay, so going back from last time again, can someone tell me how I would find the maximum height of the object?
The set the time like the speed 0. I mean speed 0. And
Okay.
then solve for the distance and then do stuff.
Okay, you're right, but we need to be a little bit more specific because we've got 2 different distances, which means we'll have 2 different speeds. So should I set my horizontal speed to 0 or vertical speed to 0?
Vertical speed.
Okay, vertical speed to 0, perfect. As long as our vertical speed is 0, we'll be at the top of our arc. And then once you've got that time, you can plug it back into your vertical distance, and that will tell you your maximum height. Okay, how do I figure out when the object hits the ground? Jan, are you still there?
Wait, Mr. Brandon.
Go for it.
Mr. Brandon, wait.
How do I find out when the object hits the ground?
Use the vertical distance.
Okay, I'm going to use vertical distance formula. I guess I'm going to leave these open to everybody because I'm not sure who's cutting in and cutting out. So I'm going to use my vertical distance formula. What does my vertical distance have to be when the object hits the ground?
0.
0. Okay, so if vertical distance is 0, we've hit the ground, and then if I want maximum horizontal displacement, I can take that time and plug it into our horizontal distance, and that'll give us our displacement. So here's one example. This is one that we already solved in class. So if we had Mic jumping, if I want the maximum height, I would take this vertical displacement, derive it to get the vertical speed, and set that equal to 0. If the vertical speed is 0, that means we aren't moving up or down, which would be at the top of our arc. So I can solve for time and get 0.5 seconds and plug that back into my vertical displacement equation in order to figure out how high we are. If I want to know when the object hits the ground, we can set that equal to 0, solve for time. You will end up with 2 times. One of them should be negative and won't make sense, so we can cancel that one out. And we're going to take this positive one and plug that back into my horizontal displacement equation up here to get how far away in meters we were away from the start point. All right, any questions on any of those three?
Sorry, I sort of missed out. My Skype crashed. Like, what did you just talk about?
That's okay. So we just went over all of the old stuff we already covered on finding maximum height when the object hits the ground and maximum horizontal displacement. So everything we're showing right now.
Oh, all right.
Okay, any questions on this one?
No.
Okay, going once, going twice. Sold. Okay, first new thing. If you want to find the slope of an arc, the slope of our arc would be a change in y over change in x. Right now, all of our equations are y in terms of time and x in terms of time, though. So what we can do is we can actually derive our vertical displacement equations. That would give us our change in y in terms of time, and our horizontal equation, change in x in terms of time. And as you guys can see, so I have 1 over dt on top, so that would cancel with my 1 over dt on bottom and give me dy over dx. Okay, so here's what that would look like.
So
Brandon,
dt cancels?
I cannot see the screen. It's just like a dark.
Okay, why don't you drop out and come back in, and we'll see if that helps.
Oh god.
Okay, so here's what that would look like. So my change in y over change in x, or the slope of this arc, would be dy over dt over dx over dt. I've got our vertical displacement equation here and our horizontal displacement equation here. So if I derive them, I'll get this. So multiply by the power, decrease the power by 1, multiply by the power, decrease the power by 1, do the same thing up here, and I've got these two new equations. So I'm going to take my derivative of y and divide by my derivative of x, and that should give me my derivative of y over my derivative of x, or change in y over x.
Brandon?
Yes.
Wait, x is the one for vertical?
So x is your horizontal.
Horizontal.
Like the VXT.
Right. So your VXT would be, you started out with some sort of a velocity vector and an angle. And we could break that apart into two different parts. So a Vx that was going this way, and a Vy that was going up.
Wait, Mr. Brennan, I'm sort of confused. Like, how'd you get your numbers for x and y, like negative 4.9 t squared plus 4.9 t and plus 29.4? Where'd you get that from?
So I've actually pulled this from the previous slides problem, where we had Mick jumping off, but I'm just using this one as an example to show you the general idea.
Okay.
If you want to solve for the slope of this parabola, so the slope of the trajectory at any point, then we'll need to take the instantaneous derivatives. That's the derivative of your y at that time, and divide by the derivative of x at that time, and you'll get your change in y over change in x, which is a slope. Okay, any other questions on this one?
Wait, sorry. For the like the dy and then dx,
Mhm.
the delta y over delta x.
Okay.
That one is, wait, what's that?
So right now, y is height and x is how far over you've gone in meters. So these are both measured in meters, right? So this is your
Yes.
change in height for every change in 1 meter over that you went from the diving board. Or your rise over run, if you want to think of it that way, which is the slope of your arc.
Oh, okay.
Okay, what we had originally was your height at any time you were plugging in, and your distance at any time you could plug in from the diving board. So if you derived it, this would give you your change in height for every second, and your change in distance from the diving board every second. If you divide those two answers, you'll end up with your change in height over your change in distance from the diving board, which is rise over run.
Okay. But why does the derivative of xt and derivative of xt same as the one that's not derived? Like it's both 4.9.
So they're actually not the same here. The difference is this t that I have here.
Oh, they're not?
Not quite. Okay, I'm gonna get rid of all my ink really quick. This t that I have here in my x of t
time.
equation is time. When you derive it, this is a constant times time, so I'll just end up with a constant. So my derivative does not have that t.
Oh, so it's just the t without the t.
Right. If you derive 3x, you would get 3, right?
Yes.
So I'm doing the same thing here. I'm deriving 4.9 root 3, which is a constant, times time. So when I derive that, I'll just get the constant.
Okay.
All right, good question so far. Any more?
Nope.
Okay, going
No.
once. Going twice. Okay, sold. And we're moving on. Okay, so if I wanted to get an equation that would map out our height at any distance from the diving board, so that's our y in terms of x, then what I can do is I can solve for t using both of our x of t equations and y of t equations, and then solve that system of equations. Okay, so I've got two equations here. Our x of t equation, which I can use to solve for t, and our y of t equation, which I can also use to solve for t. So I'm going to take our t here, because our x of t equation is a little bit simpler. And I'll take this t and plug it into our y of t equation, here and here. To get a new equation that only has y and x. Okay, so if I keep solving this, I'm going to square this, so I'll end up with x squared, 4.9 squared, and root 3 squared. Root 3 squared is 3. 4.9 squared is 4.9 times 4.9. One of those 4.9s will cancel. So it'll leave me with just one 4.9 on bottom. This 4.9 and this 4.9 will cancel. So I'm left with only the root 3 on the bottom of that term. Then if I want to simplify, I can multiply both sides by the square root of 3. If I do, that would be root 3 over root 3. The root 3 times root 3 is 3. The root 3 on top will stay.
Okay.
And then 3 times 4.9, 3 times 5 is 15, minus 3 times 0.1 is 0.3, is 14.7. Any questions on
Wait,
anything? Oh, go for it.
So for the y equation, you just substitute the one on the left
Wait, no.
with the one on the right?
Yes. So I solved for t using our x of t equation. Then I took your t, I plugged it into your y equation. So that gave us a new equation that is just y and x. There's no times anymore.
So, Mr. Brandon,
Yes.
it's just like a substitute the equation, right?
Yes. So solve for
Oh,
time, and then you
okay,
can
got it.
substitute into the other equation, and now you don't have any times left anymore.
Find derivative the equation is done.
Okay, Nikita, you okay?
Yeah, wait. So after we got the time, what do we do with it though?
Well, our
Plug
goal,
it.
right, we're going to take that time and plug it in. That way we don't have any times left in our equation. So this equation is now
Alright.
y equals negative x squared over 14.7 plus x root 3 over 3 plus 29.4. So there's no times at all anymore.
Oh, so after that we just solving for y?
Yep, so what this does is this gives us y in terms of x. If I was going to graph this now,
Oh, I see.
instead of y in terms of time, this is y in terms of x. So our graph will look like what happens to the ball, right? So this is the height of the ball as it moves away from the from whoever threw it. Or in our sample equation, this would be the height of Mick as she jumps away from the diving board. Okay, any other questions on this one?
Wait, let me just copy this real
Wait.
quick.
So you guys have all of these slides actually on both WeChat and Skype, so you don't need to copy anything down right now.
I'm gonna take a picture of it.
Go for it. Okay, any other questions? Going once?
Oh, wait, Mr. Brendan.
Okay, Abby?
So, at last, when time is all gone,
Mhm.
then why would there be a T on the left side?
So this is saying this is our y whenever we plugged in our time. But your final answer would only give you y, right? So this
Oh,
y,
so,
this y at a specific
can we-
time is just y.
oh. So we can just like ignore the T.
So we needed that t because this is our y when you plug in t will end up giving you this, but our
Oh.
output is just y. So this is function
Okay.
notation. We're not multiplying. But once you plug in that t, we don't have any times left anymore.
Okay.
Good question. Anything else?
No?
No.
Okay, we'll jump to the next one. Okay, we can also solve for what angle you would need in order to hit a specific distance away or a specific height. So I've got one example here where I am throwing an object up at 100 meters per second, and I want to know what angle I would need for it to land 50 meters away. Okay, so I was given two things. I was given the original velocity vector, so this is v total. And I can use that velocity vector over here to solve for my components. So that's my initial horizontal velocity and initial vertical velocity.
Wait. Mr. Brendan,
Yes.
where did 50 came from?
So 50 was given, 50 meters away.
Oh, no, sorry.
Initial horizontal. Okay, so I was given we have to land 50 meters away. So I know that my final distance will be 50. I also know that my horizontal distance equation is Vx times time. My Vx is 9.8 cosine theta, so I can substitute that in. Okay, whoever just spoke, mic's a little bit low, so can you try one more time?
Why is velocity 9.8?
Why is velocity 9.8? Ooh, actually it should not be. I copied that over wrong from the other picture. Thank you. Okay, does that change anything else? I've got... That does, actually. Okay, so I'll have to resolve this one, but we'll do that. Okay, so I'm shooting up at 100 meters per second, not 9.8 meters per second.
900?
I'm shooting up at 100 meters per second, not 9.8 meters per second. No, that's my bad.
Then what does does the V change?
Okay, so my original velocity has not changed. My Vx is going to change though, because that should be 100 cosine theta instead of 9.8 cosine theta. So I copied from the wrong picture. My Vy also should be 100 sine theta. We got both of those from saying the cosine over angle should be adjacent over hypotenuse. That would be Vx over V. Okay, I was told we need to be 50 meters away, so my total distance is 50. So I'm going to plug that over into our distance equation and then substitute my Vx. And I can use that to solve for time. So if I do, my time is 50 over 100 cosine theta. Okay, so I've got my time as 50 over 100 cosine theta. I'm also going to use my vertical distance equation. When we hit the ground, my vertical distance would be 0. My vertical velocity initially was 100 sine theta, so I can substitute that in. So my initial vertical velocity will go here. Okay, then I can use that to solve for time as well. So if I factor out one time here, so I've pulled out one time from both of these. After pulling out that time, I'll get t equals 0, or if I set this equal to 0, t would equal 100 sine theta over 4.9. Okay, any questions on this part? Okay.
So you just basically plugged 100 there to solve for y, or? Oh, never mind. Never mind.
Okay.
Yeah.
I took my 100 sine theta for my initial vertical velocity and I plugged that into my vertical distance equation. That way I could solve for
Oh, wait,
time.
actually, just 1 second. Is it negative 4.9 because you already derived it, or why?
It's negative 4.9 because our formula is 1/2 of the acceleration due to gravity times time squared.
Oh,
So half of 9.8 is 4.9. Okay, so I'm going to have to redo this whole line, unfortunately, but that's all right. So I've got... I'll cross multiply, I guess. So this will be 50 over 100 is 1/2, and that leaves me with 100 over 4.9 here. Okay, so I'm going to cross multiply again. So this will be 4.9 over 200. Okay, so I've got 4.9 over 200 equals sine theta over cosine theta. I'm going to break out of this for a second. Okay, so on Desmos, I've got sine of x and cosine of x graphed right now. From 0 to 90, that's my angles that I could have shot this ball at. If I shoot at a 90-degree angle, I'm shooting straight up. So I know it's got to be an angle between that. And I want this to equal, we said 4.9 over 200. So that gives us 2 points here and here. Okay, at 1.404 and 88.6. So at either of those two angles, I should be able to land where I want to land. Okay, take a new screenshot really quick. Your screen will freeze. Okay, you should be unfrozen now. I'm going to replace this really quick. Okay. So that last step one more time. We are Okay, I'm setting sine theta cosine theta equal to 4.9 over 200. If you're on Desmos, make sure that you're in degrees, not radians. And then just graph both of these equations, y equals 4.9 over 200 and y equals sine theta cosine theta, and then it will show you the intersects. If you're on your graphing calculator, graph both of the equations and then press calculate intersect. And it should give you your angle in degrees, which for us was 1.4 or 88.6. So this will be 1.4 or 88.6 degrees.
Wait, Mr. Brandon,
Yes.
how, like, on the last part, there's like a 1/2 equals 104.9 sine times cosine theta. What does that mean again?
So what we're doing is we're setting these two times equal to each other. So I got one time here that I'll plug in here, and one time here that I'll plug in here.
But the 1/2. Why is there a 1/2 though?
Why is there a 1/2? Because 50 divided by 100 is 1 over 2.
Oh,
And
okay.
then I multiplied by the cosine here. Then I cross multiplied, so 4.9 on top, and then divide by 100. Gives me 4.9 over 200.
Okay.
And then to solve for theta, we just graphed to calculate the intersects. Okay, any questions on this one? Okay, cool. So last part then. Easiest one, if I want to solve for the velocity vector, that means we're finding the actual speed of the object and the direction it's traveling at that exact moment in time. So instead of using our initial vertical velocity and our initial horizontal velocity, I'll have to use what the vertical velocity is right now and the horizontal velocity is right now, which means we're looking for a derivative, an instantaneous change in your horizontal displacement over time is your instantaneous velocity. An instantaneous change in your vertical displacement over time is also an instantaneous velocity. So that gives us your derivatives are really giving you your exact speeds of the ball at that time. And then we can use Pythagorean's theorem to solve for the magnitude and tangent to solve for the angle. Any questions on this one?
Well, let me just copy the formula because that seems cool.
Okay,
Just
go for it. Okay, while he's copying, does anyone else have questions on this one?
Wait, cop, I have to absolutely.
Okay. Just another 5 or 10 seconds or so.
Wait.
Okay, so again, all we're really doing here is Pythagorean's theorem,
Okay, I'm done. That's cool.
and then tangent to find for the angle. Okay, Abby, let me know when you're ready.
Oh, I'm done. I'm done.
But Mr. Brandon, would you mind go back that slide again? I'm sorry.
Okay, let me go back once. Oops.
Yeah, I need to see it too.
Okay.
Like for the degree thing.
Mhm.
Wait. How did you get that?
Okay, so instead of solving this one by hand, what I want you guys to do at this point is to graph it. So if you jump over here to Desmos. Um,
Oh,
If you graph both of these functions, so sine, cosine, and 4.9 over 200, then you can calculate the intersects.
okay.
If you're in your graphing calculator, you can do the same thing. So just graph y1 as this one, and y2 is your 4.9 over 200, and then press second calculate and intersect, and it will give you these intersects.
Okay.
Okay, anyone else have questions on this one?
Nope.
Nope.
Okay, I'm gonna jump ahead. All right, so that's it for today. I have,
That's that fast.
Oh, that was
it's actually
pretty
already
good.
been 30 minutes, so I do have 3 sample problems that I've worked out step by step for you guys on the homework, and then 3 blank problems that you'll need to submit on course sites. Your homework for the tension problem is also due tomorrow at 9 a.m. Your homework for the projectile
no.
motion is
Oh,
due
no.
Friday at 9
At least I
a.m.
don't-
If anyone wants to stay and get help with the last question, because I've got a lot of people that have been asking me for help, then you can stay for a couple more minutes and I'll take a look at that one. But if you guys want to leave, we're done with everything you have to be for here now. So, thank you guys for coming.
Is there anything to do now?
Bye.
Okay. So I'm going to break out of this one and I'll pull up the last question for the homework then.
The last question for weight and tension.
Right. So I'm going to look at the first 2 parts just for the setup here. Let's see if I can make this bigger.
Wait, this is on course size, right?
Yes, so this is the stuff you have to submit for course sites, but people have been telling me that they weren't sure where to go with this one.
Oh my god.
Mr. Brandon, is the 3 problems due later? Like due tomorrow?
The 3 problems for projectile motion are due Friday at 9 a.m.
Okay.
The weight and
Wait,
tension,
which 3?
so that's the ones that I just sent under projectile challenge problems. And then the weight and tension homework on course sites is due tomorrow at 9 a.m. So that's the homework from Monday.
So this one is also due at 9 tomorrow.
Weight and tension is the only one that's due at 9 a.m. tomorrow.
What about the one shown right now?
The one shown
That's
right
the
now
one that
is the
is
one
due
due at
tomorrow.
9
That's
a.m.
one of the
tomorrow.
problems.
I'm going to walk through part A and B of 6 because I've got a lot of questions. People have been sending me messages on WeChat all day today. And then for C and D, I'm going to try to let you guys solve those on your own. Okay, so I'll draw really quick. We've got 2 masses that are attached by a string here. Our mass on the table is 10 kilograms. And our mass that's hanging off the table is 20 kilograms.
Oh my god.
The first thing I wanted to know is what the total acceleration would be of the system. Okay, so what we're going to use is force equals mass times acceleration to solve for our net acceleration. So that's the acceleration of the entire system. So if I'm looking for the acceleration of the entire system, I can add up all of the forces. So to make this easier, I'm going to say that down and to the right is positive, and then to the left is negative. So the only force that I have really acting on this system is the force of gravity that is pulling mass 1, right? If there's no friction, the table is frictionless, then there's nothing else that's pulling to the left. So I could say if force equals mass times acceleration, and I want to solve for acceleration, then I could divide by the total mass. So I have my forces here.
Hey, Mr. Brandon,
Yes.
what does that, like, that a flip E stand for?
This one.
Yes.
Okay, so that's sigma. That just means we're going to sum. So I'm going to add up all of the forces. And that should
Okay.
equal the sum, so that's what happens when I add up all of the masses, times the acceleration of all of the masses. Because they're tied together, and there's no friction, and the pulley isn't doing anything, the acceleration of all of these masses are the same. So right now, if I'm looking what's happening vertically, My first mass is not moving up or down at all, right? Because the table's there. So my first force, mass times acceleration, is 10 times 0, because we're not moving at all for our first mass. My second mass is moving up or down, though. So that's 20 kilograms times 9.8 is acceleration due to gravity. So when I add those
Oh.
two...
Mr. Brendan,
Yes.
why is it not negative? Like, is it always positive in this case?
So you can choose whether something is positive or negative, but you have to stick to that choice. Ooh. I think I just messed up all of my notes. Erase really quick.
Why don't you just press Ctrl Z?
Can I undo? Nope, that's just putting my notes back. Okay, I'm going to break out and come back in. So this is weight and tension. Oops. Well.
Oh no, you missed it.
Yeah, I totally
Oh
messed this
my
up.
god.
Alright, let's see if I can salvage this. I think I moved the back picture, maybe. So let me try that.
Oh yes.
Awesome. Okay, cool. Sorry about that. So
It's okay.
your question was, why is the 9.8 positive, right?
Yes.
Okay, so you can choose your directions. In this case, I was... Nope. In this case, I was choosing for my right side to be positive and my left side to be negative.
Oh.
So our system's kind of moving together, which means we do have a mass that's moving down, but that downward motion is what's causing our other mass to move to the right, right?
Yep.
So you can choose to make that 9.8 negative if you want. In that case, your acceleration will be negative, and that negative is just telling you direction. So that would mean if you say down is negative, then our acceleration will also end up being negative, which means the same direction as that mass. I chose for this down direction to be positive because that's also moving the other mass to the right. And then my acceleration became positive, which means it's moving in the same direction as that mass. Okay. So I'm going to take that sum of the forces and divide by the total masses. So I had 30 total kilograms of mass. And if I divide that out, I'll get 2/3 of 9.8, which is 6.53 meters per second squared. Any questions on A?
No.
Nope.
Okay, there are two ways to solve B. We're looking for the tension in the rope. So let me draw out what we're looking for really quick. So there's two forces acting on mass 1 here. I've got a force of gravity that is pulling down. And then I'd have to have some force that opposes gravity, right? So that force that opposes gravity would be the tension in the string. Okay, on mass 1, I've got really only one force acting on mass 1, actually. I've got my force of tension. And normally we would have a force of friction that would be moving in the opposite direction. But we were told the table is frictionless, so there is no force of friction. For parts C and D, there will be a force of friction, and you'll have to look for that. Okay, so for us for part B, we only have tension on mass 2. So if I wanted to solve this using mass 2, I can just take the mass of our mass that's on the table, so that's 10 kilograms, and multiply by the acceleration that we just found to get the tension. So that's here. If I'm looking at the mass on the table, just take the mass on the table and multiply by your acceleration. If I'm looking for the hanging mass, then this is a little bit more involved. If you're looking for the hanging mass,
Ugh.
moving the picture again. There we go. If you're looking for the hanging mass, then I can take the force of gravity and subtract the force of tension. And that should give me the total force, right?
Yes.
My total force would be the mass that is hanging, which is 20 kilograms, times the total acceleration. The acceleration of our whole system we just found was 6.53. So that 6.53 I substituted in as 2/3 of 9.8, so that's what I got here. Because I already had a 9.8 here and I thought that would make my math easier. So I did this with fractions. If you just want to plug in 6.53 here, that's fine too. You'll still get the same answer. So take your net acceleration and plug that in. And then we can solve for tension. So my force of gravity is 9.8 times 20. So if I subtract that from the other side, I'll have 2/3 of 9.8 times 20 minus 1 times 9.8 times 20 is 1/3 9.8 times 20 negative. If I divide by the negative that I have here, I'll get a positive force of tension. So my tension is 65.3 newtons. Any questions on what we did?
Nope.
Okay. Because our pulley does not have mass, and these two masses are connected to each other, our tensions are going to end up being the same. If any of you are taking a physics class, we are not including rotational inertia, so that's like friction of the pulley.
Oh, we never did that.
So you don't have to worry about it for this. Our tensions should end up being the same here because everything is frictionless and we're not worrying about rotational inertia.
Okay.
All right. Any questions on part A or B?
Nope.
Okay. So one more time, your homework's up on course sites. Will be the weight and tension homework that I'm looking at right now is due at 9 a.m. on Wednesday. And the
All 6 questions?
all 6 questions due at 9 a.m. on Wednesday.
Okay.
And then on Friday is the stuff that we talked about today during the live session. So that's your projectile motion challenge problems. They're a little bit longer, so try to give yourself maybe an hour or so to solve it. You have 3 questions for projectile motion, and then I solved another 3 questions, long form, to give you guys examples. Those are due 9 a.m. on Friday. And our
Okay.
next live
Alright.
session will be Thursday, again at 5 p.m.
Okay.
Okay, thank you guys so much for coming. Abby,
Thank
See ya.
you.
Abby, you had a question?
No.
Oh, okay.
Will the
I have
homework
2
section be part of the video?
Will the homework section be part of the video? I will throw this on the video, sure.
Okay, thank you.